All right, we are back with some simple harmonic motion. All right, kinematics of simple harmonic motion. We have the position function right here for simple harmonic motion. We did that, I think, in the last section. And we know that the maximum position um, for simple harmonic motion is just going to be the amplitude, right? You pull a mass down to a certain point, that's the amplitude of your oscillation. That's the furthest down it's going to go. And then it should also go up to about the same amount on the other side of the oscillation, right? Okay. Velocity. Well, we know that in physics one, it was really kind of tough. You just had to know these equations, but in physics C, we can now just take the derivative to get there. So I can say that the velocity is equal to negative a omega sine omega t plus phi. Okay. And my maximum in this case is going to be v equals a omega, okay? Because the maximum occurs when the trig function resolves to 1, okay? Or negative 1, right? I guess negative 1 would be the minimum, right? Or I guess, well, because you got a negative right in front of there, right? Then I guess it would be when it resolves out to negative 1, but it doesn't really matter, right? Um, and so yeah, there's that. Um, and so normally in physics one, you would have to look at the position graph, and to get the velocity graph from that, you would have to look at the slope. Okay, and I'm still going to do the same thing, but as long as you also recognize this is a cosine wave, this is going to be a sine wave, and then and when we differentiate this again to get the acceleration, we're going to end up getting acceleration is equal to negative a omega squared times cosine of omega t plus phi. Okay, and the maximum acceleration for this is going to be a omega squared. Okay, and so when I do the curves for these, what the graphs are going to look like, okay, this is going to start at 0 because my slope initially is 0, okay, and then my slope here is negative, okay, and it's actually the greatest the slope's going to be. So it's getting more and more and more negative, and then it's the greatest it's going to be, and then it's getting less, less, less negative. Okay, so when I do this, it's going to look kind of like this. Okay, for the first segment, and then you're going to notice it goes back. It eventually becomes 0 at 1/2 of t, and then it's going to curve back up just like a sine wave does. Okay, um, and then the acceleration, okay? To get the acceleration, all I have to do is, again, this was a cosine curve, this is a sine curve, this is going to be a cosine curve again. If I'm looking at the slope, this is a maximum negative slope, so it's going to look something kind of like this, and then it should go kind of like this. Okay, that's how your acceleration curve is going to look. Now, another thing that's important that I want to point out really quickly is that your maximum equations. This equation looks like the equation v equals r omega. Okay, look, do you see that how r is kind of like, or a is kind of like r in this case, right? And then this equation down here looks like um, a equals r omega squared. Okay, so it looks kind of like that for that, and this is um, uh, centripetal force or centripetal acceleration, right? Because normally you could do v squared over r or r times omega squared, right? So those are two equations for that. Okay, that's kinematics of simple harmonic motion. Nothing too crazy. Just wanted to kind of show you that. Okay.